good afternoon to everyone. I'm Etienne, and I'm representing the Groundwater Division from the Eastern Cape this afternoon. I'd like welcome you all to this talk. It's a very topical one on water treatment for small potable systems. And it's entitled Selection of Small Water Treatment Systems for Potable Water Supply to Small Communities. Something that is of interest to a lot of us in the industry. But before I hand over to our guest speaker, I'd just like to make two announcements. One of them is, please, if you got any questions, please type these questions into the chat box. And the second announcement is attendance. Please type your name, comma, surname, and your affiliation. This makes easy for Yolanda to do the affiliations after this talk. I can see the talk is very well subscribed, and I'm now going to hand you over to Chris. But before I do that, something about him is Chris Swartz is a water utilization engineer from Durbanville who has his own consultancy. He's a registered professional engineer who specializes in water supply and the treatment of drinking water, as well as water reclamation and reuse. After graduating as a consulting engineer at University of Pretoria, he enrolled in a master's in water utilization at the same institution. He's gained experience at the CSIR. He has his own private consulting practice called Chris Swartz for Water Utilization Engineers in Mossel Bay, which he started in '91. He has since opened an office in Durbanville. He has over 28 years in the water industry, and in 2007 he co-authored a Water Research Commission guidebook on the selection of small water treatment systems for potable water supplied to small communities. He did this along with Stellenbosch University and Rand Water. This afternoon he'll be taking us through aspects of that particular publication. Now I'd like to hand you over to Chris Swartz. Chris, can you go from here?
Mute myself. Okay, sorry about that. Thank you very much, Etienne. And good afternoon, everybody, on this Friday afternoon. Thank you also to the Groundwater Division. Sorry, just want to grab some water here. Thanks to the Groundwater Division for hosting me this afternoon, and I look forward to sharing some of the work that we've been done on small water treatment systems. Thank you also to Yolanda for facilitating this session. So, as Etienne has mentioned, I've been involved in the water treatment, water purification field for a number of years. A lot of interesting projects that we've done over the years. And I'd like to share some of the technological aspects of that. So what I would like to discuss this afternoon, just briefly have a look at the water sources and then water quality aspects, specifically in South Africa. And yourselves being from the Groundwater Division, I'm going to focus mostly on groundwater quality after that. The guide that Etienne mentioned that we drew up for the Water Research Commission was for all sorts of water qualities, but as I said, we will look at more specifically at the groundwater aspects. Discuss some treatment options and then classification of raw water types, which we need to further look at options and to establish best options for a treatment requirement. We look at the water quality standards that we have in South Africa, and then go through the process for selection of treatment options according to the guide that we drew up. In addition, just by way of interest, I'll share some information on advanced water treatment processes, and a number of these are required for treatment of groundwater because of the unwanted substances dissolved or particulate that you get in the water that you need to get rid of. And then in the second half, I'll just show you the water technology information sheets, how it's been drawn up, how you can use it, and we'll go through the most important ones of those. So in South Africa, as in most of the other countries, but some other, the ratio between surface water and groundwater just differs quite a lot in various countries. But we all have surface water, groundwater, surface water that you get from dams, or also called reservoirs by the Americans, and rivers, and then groundwater that you get normally out of boreholes, springs and wells. Other sources of water for drinking water is seawater desalination, and myself being based in Cape Town, I've been involved with the new seawater desalination plants that were constructed during the past 3 or 4 years quite intensively. Small plants, and this was due to the serious drought that was experienced in the Western Cape 2016, 2017, 2018, working towards day zero, as you will recall. And then a further source of water is to treat your wastewater, which you would normally discharge. This is mostly treated domestic wastewater that you would normally discharge to river or to streams, and treat that to, it can be various options, secondary treated wastewater, which is often used for irrigation, but you can go further with further technologies and then get direct potable reuse, as has been practiced in Windhoek for more than 50 years. Also, Beaufort West was the first South African plant with direct potable reuse from treated wastewater. And then it could be also indirect potable reuse. That is where you put the treated water then from the wastewater into a dam or back underground through managed aquifer recharge. And then later on, you can withdraw that water again, treat it as normal through a water treatment plant, and make it available for drinking water. The last one is what we call de facto reuse or unintended reuse. That is where we have the situation, if you have poorly performing wastewater treatment plants, as we have many of in South Africa, and the quality of the wastewater that they discharge to river these plants has a big impact on the downstream towns that withdraws and abstracts this water for potable use and have to treat it. So those are the main sources of water for drinking purposes. We're all familiar with the hydrological cycle or the water cycle. This just shows the various contamination points where water sources can be contaminated, and that the water quality that you withdraw then for potable use, what we're discussing this afternoon, will be undesired and can have either health impacts which can be acute, mostly through microorganisms, or it can be chronic, mostly from chemicals over a long term of exposure. So you can see the farming activities, industrial activities, these can also all have, and even the human wastewater treatment plants, all discharged into your water courses and can cause impurities landing in your water, which we'll have a look at just now. So on this map of South Africa, we can see there's basically 3 distinct zones that we can divide the country in. So central to northern zones, your inland waters, basically surface waters, would contain turbidity, like in clay turbidity, mud, surface, ground runoff that lands into the river. So it can be very high turbidity if it's a high intensity storm, normally low in color as a result of organics. So, and that water is fairly easy to treat. Chemical treatment has been used for many years for doing that, but there's a lot of new technologies coming into the market now. In the southern coastal zones, indicated there up to Cape Town, you may have seen the river waters. There is a yellowish to brown color, the natural water. And that's mostly organics in the water, natural organic matter, or NOM, that gives rise to high color. Now, this color is not necessarily a problem or a healthy risk if you ingest that water, but there's other secondary risks. If you chlorinate that water, you can form carcinogenic compounds like trialomethanes. Turbidity normal, quite low. And then the third one is in the west coast and actually the whole Karoo area as well, where we have high TDS groundwater. So now you're getting your brackish water or your high salinity water. That causes both aesthetic problems, the taste is not good, and also it can cause some health problems depending on the concentration. So that's the main quality divisions that we have in the country. In terms of groundwater, we saw on that previous slide, it's mostly dissolved salts that causes the problem, total dissolved salts or TDS. And this can be made up of calcium magnesium, which gives rise to hard waters. It could be chloride as well, sulfates, nitrate, and we'll discuss each of these just now in a while. Fluoride, iron and manganese is often a big problem, especially aesthetic. When you oxidize the iron precipitates give rise to a very fine precipitate with a reddish color that stains everything, your laundry and your household appliances and so on. Arsenic, not so much historically a problem in South Africa, but there are areas now where they're picking up arsenic. A big problem in India, Bangladesh, and those countries. Colloidal material, which is typically your fine particles, too fine to settle out on its own. So you also need to enhance that with chemical coagulation, or you need membrane systems, as we'll get to in a while. Then you can also get some organic substances, and this is mostly from industrial pollution that can land up in the underground. And then something that's been on the forefront very much recently is the chemicals of emerging concern, or the so-called CECs, also called micropollutants, priority pollutants, and so on. These are the very fine, very low concentration substances, hormones, pharmaceuticals, pesticides, and so on that land in the water and that can have very negative long-term effects. We'll come to that just now. In terms of microbiological water quality, so we all know that we don't need any pathogens in the water, that's disease-causing organisms. And these can be either bacterial in origin, it can be viruses, it can be parasites, typically Giardia, Cryptosporidium, and it can be waterborne, water carried. There's lots of routes that it can get into the water and that it can cause a health risk. This is mostly acute, so if you drink water with high amounts of pathogens in, you'll become very ill, and if you don't see a doctor and get rehydrated, then you can also die. Typically, cholera is a good example, cholera outbreaks that we've had in the country. Now, in terms of measuring whether we have this pathogenic pollution or risk, normally we do that by E. coli, which is part of the coliform group. And it can be also done by fecal coliforms as well, more done for wastewater. E. coli is more used in the water treatment field. Okay, just a little bit something about these chemicals of emerging concern. As I mentioned, they've got different names you might have heard of, is the EDCs, endocrine disrupting compounds, which really causes problems with the hormonal systems in humans. DBPs, that's your disinfection byproduct. So you disinfect the water to kill your microbes and your pathogens, But in the process, you cause disinfection byproducts to form, which can have a health effect on humans if not regulated. Trace organic compounds is the one at the bottom there, priority organic or persistent organic pollutants, and PPCP is your pharmaceutical personal care products that you get, even your creams and things that you put on that can land in the water and have a negative effect on humans. So the CECs are not new chemicals, but it's newly concerned the effect that they can have. And there's lists and lists, very long lists of these organic chemicals. The US EPA develops quite a lot of these as they carry on. So the groupings, I mentioned pharmaceuticals and vet medicines, personal care products, flame retardants, perfluorinated and brominated substances, pesticides, herbicides, and so on. So these are being very much researched in a project that we did for the Water Research Commission recently. We identified a priority group of 10 of these, trying to cover all the main groupings, which you see on the left-hand column in the blue. These will be industrial chemicals, pesticides, and so on. So in the right-hand side, there are names that would look familiar to you: atrazine, simazine. There's a number of the antiretrovirals as well, anti-epileptics, antibiotics, and so on. So these are, I'm just mentioning that because this is being regulated through SANS 241. They're not listed in a table yet, as they are in the WHO, Australia, and the USA, but that is bound to come. And we are working on providing SANS 241 with some of these lists for future reference. So legal requirements, we're working on SANS 241. The latest version is the 2015, but they're working on the new one and it should come out next year. So the latest version will probably be SANS 241 of 2021 then. And then obviously where we're not regulated in terms of the CECs and so on, we use EPA, Australia, WHO lists and other regulations. So I think you should all be familiar with the SANS 241. It's what it looks like. And then just to show the tables, there's one specifically for the microbiological determinants, E. coli, protozoan parasites, coliforms, somatic coliphages, and so forth. There's also lists for the chemical, physical determinants, grouped under micro and macro determinants, physical and so on. So things that are important is your conductivity, which is your measurement of the salinity of the water, turbidity, which is a major operational parameter for controlling your water treatment plant. And then the other ones are your metals and your salts and so on, which we will discuss just now as well. In terms of organics, we've only got TOC as a major pool of organics, and there's a lot of work going on to do this in a bit of more detail, to look at various types of organics and what the effect of those could be. Okay, if we can have a look at the treatment options for low turbidity, for the different water quality types. So the first one would be low turbidity, and I'm not going to go through in detail on these, but I'm just showing how they're structured. So in the top row there, you would see the classes, and below that would be the different options for the quality of water, low turbidity in this instance. So there would be pre-treatment, chemical treatment, filtration or particle removal, disinfection, and then if there's any post-treatment. For turbidity or filtration that you can use, there's 4 different types: direct, upflow, pressure filtration, direct series, slow sand and so on. You'll see there's not normal rapid gravity in here because we're looking at low turbidity water. So you can do that by other processes that you don't have to first add some turbidity through clays and so forth. For water-containing organics or water with color, visible color, there's quite a few options to use. So you can use any of these routes to make up a process configuration to suit your needs. And we'll show you how you can decide on what would be the best option for a specific situation. And that is what the guideline that we drew up for the Water Research Commission is all about. I saw in the invitation for the for this webinar that was sent out, there is a link to the report that I'm taking most of this information from. So if you want to obtain a copy of that, you can download it directly from the invitation. Then there's one for brackish water as well. Now, as you know, to remove salts, your chlorides or your hardness, calcium, magnesium, or your sulfates and so on, you can't use ordinary chemical treatment. That won't help. So you would need something like either membrane filtration, ion exchange, perhaps distillation, solar distillation. There's a number of options that you can use for that. And so these diagrams show you the options that you can use, including chemical treatment, phase separation, and so on. Chemical treatment is more just upfront treatment to remove other stuff before you desalinate. In the yellow boxes at the bottom here, there's important notes on the treatment processes and things that you should be aware of when you try to make a selection. Then iron and manganese in groundwater specifically, as I mentioned earlier, is a big problem. We get that all around across the country in certain areas. It can cause a lot of aesthetical problems in distribution networks and at consumers. So, and at high concentration, obviously the metals also pose a health risk. So the most common one would be first to oxidize your iron, get it out of solution, and then filter out the precipitate that's formed after you've oxidized it. But we're getting to that just now. Options for softening of hard waters like we have in the Karoo, for instance. Many of those towns, you will very distinctly taste the hardness of the water. But apart from that, the hard water causes calcium carbonate and calcium sulfate deposition on your heating elements and reduce the life of those kettles, geysers, and so on substantially if you use hard water over a prolonged period of time. Nitrates in your groundwater can be a problem as well. You can get a lot of health effects, especially with young persons, the blue baby syndrome, where your oxygen transfer capacity in your blood is affected by the nitrate, and then you can have a lot of health problems in that regard. So there are technologies for removing the nitrate. You can do it biologically, or by ion exchange, or even membranes you can use successfully for that. So in terms of fluoride, before we look at the options for fluoride, I think you're familiar with the causes of high fluoride in the water. Anything above about 1.5, you can get serious fluorosis. You can get your mottling of the teeth, brown formation on the teeth, but you can also adversely affect your skeletal system and get brittle bones and bones that breaks very easily if you've got drink water with high fluoride over a long period of time. So if you go up the West Coast, places like Gurries and thereabouts, if you have a look at the people there, you will notice their teeth looking not all as bad as this, but you can definitely see some mottling on the teeth. So there are fortunately solutions for high fluoride water. Activated aluma is a very popular one that's used, but you can also use membranes. Membranes for most of the treatment options is a solution, although you must bear in mind you're causing a brine that you have to get rid of. And it's also high energy requirements for operating a reverse osmosis or membrane treatment plant. Okay, so these water quality parameters that we discussed, they can be grouped into different classes, into different groups, according to how important it is to remove them from a health perspective and aesthetical perspective. So Group B and Group A. Group B is your nitrates, fluorides, sulfates, chlorides. So these are typically more in your groundwater. Group C, cadmium, copper, getting to your more heavy metals now, and then Group D, which is more aesthetical, hardness, and your iron manganese. So what we did in the manual to assist with selecting of treatment processes, I just need to watch the time as well, is to group them. For instance, if you have a look at turbidity at the top, you can classify it as very high turbidity, higher than 500 NTU, high turbidity between 50 and 500, medium turbidity, and low turbidity. The reason why we do this classification of all the various quality parameters is because that really dictates what sort of treatment process you're going to use. Okay, so and then it continues on the second page. We discussed about the SANS 241. I just repeated it here because it contextual. This is where really you would start looking at what is the requirements for. If you take a water, you want to know how to treat it. Then you'll measure the turbidity and the color and a lot of parameters. And now you need to see, does that comply or do I have to remove more? And you will use the SANS for that. Now the treatment selection process, basically a 5-step decision flow start. In step 1, you will identify first the main water quality problems. If you want to get a good, clean, healthy water, you want to see what is in the water that you need to remove. Then you need to put them into main treatment classes or types, that previous table that we saw. Then you go to your available treatment technologies. You draw up, compile a treatment configuration or a number of them that might be able to treat this water. In step 4, you look at the technology information sheets. There, for each technology, it tells you things like what is the maintenance requirements, what's the operational requirements, how complex is it, what is the effect on the public community sort of interaction, and then very important, obviously, cost as well. What waste streams do you produce? How can you get rid of that, and so on. We'll get to that just now. And the last one is you compare all the ones that you put on your short list, and then you make a decision on which will be the best for your specific situation. So in step 1, you use these tables. So in the right-hand column, you'll fill in your value, and then you'll determine, for instance, it's a low turbidity, high color, low brackish, but moderately hard, and so forth. And then you can go on to step 2, and you've got this table here where you can see if you've got a table, say you've got a medium turbidity, you see you can use chemical treatment, you can use fine filtration, and you can use membrane filtration, or electrical and magnetic treatment, more the advanced type of technologies, and so forth. You can go through your whole table. Based on those that you have marked, you can draw up then a list of technologies that you could use. And this is your complete list of technology, or not complete, but it's a quite comprehensive list of technologies. And you select from that previous table which technologies you would look at. This is your information sheets with the information on each of the technology. It will tell you the purpose and status, what the different alternatives are, what other technologies. Excuse me. Summary of key features. It describes the process as well as with a flow diagram of technology. Illustration. It can give you, if there's any limitations on the performance, it will be listed. It can tell you whether it's, whether there's any performance limitation. Do they only work for large plants, only for small plants, or any type of plant? Recommended capacity. You can look then at operational requirements of that technology, maintenance, infrastructure requirement. Things like impact on failures, energy requirements, obviously important. So the costs include both capital costs and operating costs, so that you can see if you try to establish what would your life cycle cost be over 10 or 20 years. Typical treatment process configuration. It also provides in row 16 the examples of South African installations. So if you want to go and have a look at the technology to see, get first-hand experience. I mentioned a bit about the socio-economic impact, and then we also listed which universities or research organizations are doing work on these technologies. And then you, to make your decision, you compare the available technology that you've listed, and then you can do for yourself a own cost analysis, cost-benefit analysis to see which will work best for your situation. Okay, I'm briefly going to look at some of the special treatment processes. That would be things like activated carbon adsorption, softening, defluoridation, and so forth. But one that we quite interested in for groundwater then also is your iron removal. As I mentioned, firstly, you want to oxidize the iron. You can oxidize it either by aeration, which is a bit slow, but it works. Or you can use an oxidant like chlorine, ozone. There's different oxidants that you can use. You can also use what they often use is sand, which they use called green sand, which you get magnesium dioxide coating forming on the sand. You can do that with potassium permanganate, for instance, and then that enhances your iron removal, and you can use such a green sand filter effectively for that. So the problems with iron is metallic taste, discoloration of some of your household and industrial products, staining of clothes, clogging of pipes with iron bacteria. Of course, iron bacteria like this water very much. And then it creates red water if you wash out this iron bacteria. So a lot of staining, aesthetical problems mostly, but also aesthetical in terms of taste, metal taste. So I'm not going to go through the chemistry, but suffice to say that you need to oxidize and then filter out the very fine precipitate, which is shown graphically in these slides. For fluoride removal, you can, looking at reducing normally to less than 1 milligram per liter. You'll also record that there was incentive, or not an incentive, but a development by the government about 10 or 20 years ago to actually dose fluoride to some water sources with very low fluoride concentrations. And that is for protection of the teeth, especially for small children. but there was a lot of resistance to that initiative that the government tried, and that was never implemented in South Africa. A lot of countries overseas did that, but they did since stop doing that as well. But there are still some countries that do fluoride addition to the drinking water. So some of the technologies to do that's activated alumina or dosing with aluminium sulfate. You can use membranes, reverse osmosis, electrodialysis, and also ion exchange. For nitrate removal, I mentioned briefly chemical removal. You can do it biologically, and then again your membranes and ion exchange. Okay, so I'm really, time has caught up a bit with us. So the following slides is just further information that is of assistance with these advanced treatment processes, so that you can just get a better grasp of what the processes are about if you're not familiar with them or do not work with it on a regular basis. So membrane processes, it's a barrier, so your water can either go through or not go through. So you can't get a poor quality water as not going through. So if you clog the membrane, you need to wash or to backwash the water. But you get a continuous cleaning of the membrane. And depending on the quality or the concentration of your salts, like seawater with a high concentration of salts, you'll get less water going through your membrane and higher rejection. So the different types of membranes on reducing pore size, but increasing pressure that you need to get it through is microfiltration, ultrafiltration, nanofiltration, and then reverse osmosis, which is basically your very finest. You can see in this diagram what you can get through and what is retained on each of those. So on your microfiltration on the top, it will it won't let through your colloid, so you'll remove your colloid material, so or your fine turbidity and so on will be removed by a microfilter, and some of your bacteria as well, say 70 or 80%. Ultrafiltration, you can remove some of your macromolecules in addition, and some viruses. Nanofiltration, you can reject your divalent salts, in other words, your calcium, magnesiums, and so on. So that's why they often call the nanofiltration your softening membrane as well. And then your reverse osmosis basically only let water through. It even keeps out your monovalent salts like chloride, sodium, etc. You can see on the right-hand side, decreasing pore size, so very little pore size, almost no pores here, and here is bigger in this one. And you need much more pressure to get your water through the oral membrane. So that's just a typical figure to show the relative sizes of the materials that you can filter out and help you to decide which of your membranes would be the best to use. So some membrane configurations, you can use capillary, like those straw types there. You can use flat sheets. You can use spiral wound, which is shown in these following slides. That's where you wrap up over a cylinder your membrane, and you get much more effective use of space. Your water rejects the salts and it lets through your water. For arsenic removal, there is a number of technologies as well. As I say, I haven't worked with that myself too much because we haven't had situations where we needed arsenic removal, but it is becoming more focused on now when you get new water sources, especially groundwater sources. So oxidation and sedimentation, it lists different types there, technologies, and then advantages in terms of cost, operational simplicity, and then disadvantages as well. Does it produce waste streams, sludges that you need to get rid of, and how serious is that? So advantages and disadvantages of membrane systems. As I said, one major problem is your brine stream, your concentrated salts. You need to get rid of that. You can just dump it in a river. It is not environmentally good to do that. So you need to do it in a very well and controlled method. So some examples of ultrafiltration and microfiltration, particle removal, pathogens, ultrafiltration, some finer treatment. And you can see there what it looks like typically. Nanofiltration, softening, mostly if you want to go all the way to also remove your monovalent ions, you would use then reverse osmosis. Electrodialysis, just where you use the electrical potential as your driving force, and basically you can now distinguish between different types of anions and cations on what you would like to pass through your membrane or not. Activated carbon, basically adsorb organic material. You can remove things like your micropollutants that way. You can do color removal to an extent if your loading is not too high. You can remove chlorine and other products as well, but mostly for organics. It's got a very high surface area, and there's a lot of micropollutants that can be adsorbed to the surface of the material. So a granular activated carbon is in granular form, like a filter, either pressurized or normal gravity filter. Powder activated carbon, you dose into your water, and your impurities, your organics, is adsorbed onto the organic carbon. Ion exchange is where you've basically, you can use that for exchanging your calcium ions with sodium ions. So often used household as well for softening waters. So if there's a municipality that does not soften the water, you can put in your own softening water, which is mostly ion exchange systems. This just described. I have to run through this because of time. We want to still allow some time for questions. And then advanced oxidation process is very important, where you create a hydroxyl radical, which is very powerful, and you can destruct organics or break down large organic molecules into smaller chain molecules, which is more readily adsorbed in your activated carbon, for instance. Or you can totally oxidize those components. UV light is often used as a disinfectant as well. It's particularly of importance where you need to remove your parasites, Cryptosporidium and Giardia, which is chlorine resistant. So if you chlorinate the water, you won't kill those parasites. And then you have to apply UV, either alone or in combination with things like peroxide, ozone, and so forth. So ozone, as you know, is formed by splitting the atoms or the molecules, and then you get O3 forming, O2 that you split, and in the process you get O3 forming, which is also a very powerful oxidant as well. Those are just the different types of ways that you can generate the ozone. And this is just a small system, typical what it would look like for a ozone plant. So Etienne, this is this took a bit longer. This is the end of part 1. So I'm just going to change the slides to the second part, but I'm basically, the second part of the presentation shows all the technology information sheets. So I'll just use one or two of those to show you typically what the information would look like there, not go through all of them. I believe you'll be getting the presentation afterwards, then you can have a look at all the different technologies. But for now, we can just have a look at one or two of them, and then maybe if there are any questions, I can try to answer those.
Chris, thank you very much. It was a very interesting talk that you gave there. I think you went through a lot of stuff about water treatment, and you went through it in a very fluent and a logical manner. I found your flow diagrams and your tables very easy to assimilate. I also found aspects on your chemicals of concern to be very interesting. Are we going to take some questions at this stage? Yolanda, can you perhaps advise?
I think that would be fine, Etienne. I don't think we have that many questions yet, so I think it would be opportune for this 5-minute break to address the ones already posted.
Okay, thanks. I picked up one earlier on. It was from Melissa Lindner-Strauss, and she wants to know how many commercial labs are available in South Africa to test for the EDC and pesticides, and what is the cost of such tests? Can you give us some feedback, Chris?
Yes, thank you, Etienne. Hi, Melissa. So there are a number of laboratories that can do the micropollutant testing or the CEC testing. Unfortunately, most of them are either at universities or at water boards, so they're not independent laboratories that can do these as a routine monitoring. But a lot of the laboratories, of the commercial laboratories, are positioning themselves now, or have already done so quite recently, to be able to do this. So, you know, Mgeni Water, for instance, can do University of Free State, Rand Water, University of Pretoria to some extent, University of Stellenbosch can definitely do University of Western Cape. So there are enough laboratories that can do these analyses, and it is expanding in terms of the commercial laboratories. And then also it is quite expensive, as you say. The normal would be if you have a water and you don't know what to look for in terms of your CECs, you could do a qualitative scan to see what is in there, and then you can quantify those that you detect. So you can scan maybe for 200 of these chemicals and pick up 5 or 10, and then you can focus on those further. I won't be able to give you a number, but it is rather expensive.
Okay, thank you, Chris. Melissa, I hope he answered most of your queries. Chris, if we can slot in another one from Greta Pergram. She wants to know, how do you recommend removing substances such as hormonal and prescriptive medications that are increasingly found in wastewater discharges? Can you maybe just elaborate on that, please?
Yes, so basically in terms of you know, the process configurations that you can use, your main processes would either be your granular activated ozone plus carbon, which normally is your biologically activated carbon, BAC, followed by GAC, or you can go the reverse osmosis route, RO, and then normally advanced oxidation process is used as well for just finally causing oxidation or destruction of these very low concentration organic substances. So there are technologies available. It's already been applied worldwide, and even in South Africa, a lot of these technologies are in operation already.
Okay, Chris, thanks. Ilanda, can we take more questions, or are we ready for the next part?
Etienne, this is another question came in, which is very interesting, but I think let us handle that at the end, because I would love to see what Chris's next presentation is about. I think let us keep Sizwe's question for after the second part, and then we can follow with other questions.
Okay, I have picked up on Sizwe's. Okay, I have picked up on Sizwe's question, so I'm going to hand back to Chris then.
Thank you, Etienne. Is this slide with heading technology information sheets, is that on the screen now?
Yes, I can see it, Chris.
Okay, great. So I'll just continue. So as I mentioned, I'm just going to show one of two of these slides, or we can run quickly through a few of them, but just discuss one or two. So this again is your listing of technologies. Okay, continuing, sorry, on the second page there. So basically a grouping of technologies, membranes, disinfection, absorption, and so forth. And then under those, more specifically, the types that you get. Okay, if we have a look at oxidation, so this is typically what it would look like. So, sorry, I must perhaps just go into presentation mode. The purpose and status of aeration, typically for iron removal and stabilization, it's a proven technology. Other ones that you can use as alternatives are chlorination, ozonation, green sand filtration. Some of the key features, it's low cost. Aeration is a low cost option. It's non-chemical. It's a simple method for oxidation of iron found in groundwater. And we've successfully used aeration followed by filtration in places like the Western Cape, Albertinia, and so on. And it works well. It's got low operational and maintenance input and low operational costs as well, because it's aeration and no chemicals are used. But it's not quite as effective as your chlorination or the other oxidants. Description, then it tells you exactly what not exactly, briefly what the process entails. It shows some of the illustrations there that shows how you can aerate the water either through a mixing race falling down or a cascade tray system that you can use. It gives you performance limitations there, only effective when your pH is higher than 7.5, for instance. So you need to increase your pH as well. Otherwise, often the pH of this water coming out of the boreholes could be 5 or 6. And at that pH, you're not going to achieve much when you use aeration as your oxidation option. A recommended capacity up to 2.5 megaliters per day, so more on the small treatment plants. Operational requirements in terms of operators, what they need to do, maintenance requirement. Your spray nozzles obviously have to be kept clean. Infrastructure requirements, and so forth. And then there's a process configuration, just showing what processes or steps are involved. Examples of South African installations, and then a number of things regarding socio-economic impact. So if you're in a very rural area, will you be able to sustain, or will this be a sustainable option? Things like that. And then you can also see research and evaluation, some institutions and even researchers that can be added there. Same for chlorination. I'll just briefly go through ozonation. You can see your ozone generator is your main item there that you need to install. But you get very simplified systems of those. So that works well. Green sand filtration, you can get that basically commercially. The filter medium, that's used quite a lot. Potassium permanganate. So I just want to give you the drift of what these technology sheets look like and how you should use them. So in those steps 1 to 3 that we did previously, you look at the different technologies, your water quality, what do you need to remove, and then you come to these sheets and you look through at all the various characteristics of the technology, make notes of what the downsides is and what the advantages are, and then you can make a selection from that. Chemical treatment, you see there's a big description here because there's a lot of applications for chemical treatment. It can be color removal, turbidity removal, heavy metals, and so forth. Yes, and limestone contact stabilization that was done in the Western Cape, a lot of small applications on groundwater, often together with iron removal plants. Phase separation, then we're looking at the settling, high rate settling. If you've got need a small compact system, perhaps in a container or a small plant. Batch sedimentation, often you could get a 10,000 liter or 15,000 liter tank that you dose chemicals into. You give some stirring for flocculation, then you leave it for 24 hours or for a certain time to settle, or 8 hours overnight, and then you can just decant the next day the top water, which should be fairly clean. Often used on farms because very little input required for that. Solar distillation, I think you might have seen this concept where you've got a little box with a glass top, and in the sunlight areas you would get distillation and evaporation and distillation on the surface, and it runs down. Obviously your output is quite low, but if that's your only option in a very brackish water, then that's normally very welcome. Fine filtration, bag filters are often used for small installations, cartridge filtrations, off-the-shelf cartridges. Membranes, a lot of options available in terms of membranes. And if you want to do a reverse osmosis or an ultrafiltration system, then you can just see what are the options and prices available in the market, and what's the sort of backup service you get from the technology provider. Ultrafiltration, I mentioned that. RO, often used. Nanofiltration, electrodialysis. I haven't seen a lot of those in small household waters or water treatment for household use, more industrial use. But there are the options of doing that. Disinfection, the one most often used, gas chlorine. For small systems, sodium hypochlorite, liquid dosing that we've got here works well. Because of the gas chlorine, there's a lot of hazards with handling that, health and safety hazards. So hypochlorite and even granular chloride, like your typical HTH that you can use to make up a solution, and then you dose that solution as well. On-site chlorine generation, typically from salt. You can do that, the same principle as the salt water swimming pools and chlorinators, where you generate through an anode and a cathode and electrical current, you can generate your own chlorine. Mixed oxidants are some of the variations that you can do. Solar pasteurization, that is really, if you don't have other options, you can just fill a bottle with water and let it lie in the sun, and the water will at least be pasteurized to some extent. This isn't the same. You can see it alternatives there. Boiling is another option that you can do if you don't have any other options. So not the best and most advisable options, but they are used in certain areas, in developing areas. UV disinfection, often used. Problem with UV, you don't get a residual, so you don't get a long-lasting effect of your disinfectant, and you can get regrowth again afterwards. Adsorption, I showed you in the previous presentation the different types, your granular activated carbon in your GAC filters. You can even put a layer of GAC on top of a sand filter as well. Then your powder activated carbon, which has the advantage that you only have to dose when needed. Like for instance, the Cape Town waters, certain times of the year, they have lots of taste and odor problems in the water, and then they would dose powder activated carbon. But once that outbreak is stopped again, then they don't need to dose the PAC, and then you can basically just not use that anymore until the next incident. Activated alumina, we discussed for your fluoride removal, for instance. Ion exchange, information on the ion exchange systems that you can find there. Specifically then this one for nitrate removal. A lot of this research work was done by the CSIR in Pretoria, so these are very applicable or appropriate systems for local conditions. Okay, and that's it from my side then. Etienne, thank you very much, and thank you to everybody for listening. Etienne, you're muted.
Sorry. Thank you very much, Chris, for a very interesting talk. I think we've got time for a couple of questions, and there's one from Sizwe Mabalisa. I told him I'd get back to him. And he just said that in deep rural communities, I think where there's no power, no electricity, these people have to rely on drinking water from rivers, unprotected sources, and they've got to boil that water before drinking. How effective is this, and what other cost-effective solutions can they explore?
So boiling is effective. Very important that when you boil water, don't just bring the water to boil and then drink it. The water must boil vigorously for at least 5 minutes for you to be able to kill the pathogens and the unwanted microorganisms in the water. So obviously that's energy intensive in terms of you have to make a fire for that. For where you don't have electricity, slow sand filtration is a good option that also gives you some disinfection as well from the smooch decker, which is formed on top of the filter. If you've been filtering for a certain amount of time, this layer builds up and you get disinfection of your water as well. So there are technologies, even membrane systems like UF. They've got systems that are used in Sri Lanka after the tsunami a number of years ago, that you pour the water into the top. You get very slow trickle of water coming out at the bottom, but if that's your only choice, then it's a good quality water coming out. And obviously, if you apply some pressure at the top, then you can get more water and quicker the water comes out. But yeah, there are a number of systems for gravity use.
Thanks, Chris. Two other questions. I think there are some rural communities where there's no access to power. And are there not sort of like passive ways which the water could be treated? I'm looking at a question here from Sumaya, Israel. She says small communities, in the context of the previous comments, there isn't always electricity available. Are these systems robust and low cost? Can it be constructed from locally available materials in rural communities? Is your talk more related to municipal treatment or as a small rural communities may require point of use treatment methods, filtration systems within the household. Can you just elaborate on that, please?
Yeah, so what I didn't specifically look at for this presentation was your household systems in terms of clay pots and things. That's used quite a lot of, especially in your areas where you really don't have any electricity, and then they develop and research a lot of those types. I was involved in one of those projects, so that's very good work that they're doing. So what I was more concentrating on today is groundwater for small applications, a couple of households maybe. I wouldn't say to municipal scale, but small community. And yes, it is true that it is a problem if you don't have any electricity available. But for the previous question, I did mention some of the things that you could do.
Okay, thanks, Chris. One more here, I think, from Makwata. He just says, since the small rural communities are using underground water, such as wells and boreholes, as a water supply for drinking purposes with regard to leakage of carbon dioxide, which might be stored or contaminate underground water, what are the technologies, mitigation measures that could be used to prevent or reduce the carbon dioxide as the contaminants leakages to the underground groundwater? I think, Makwata, you might have to explain this, activate your microphone, and maybe explain this question. Chris?
Yes, I must say I don't have specific experience on the CO2 component in these systems and how it contaminates the underground water. So if he can maybe explain, then it would be interesting to hear what the issue is there.
Okay, are there any more questions from anyone out there? Either activate your microphone or type it into the chat box. And we pushed you, we wanted this talk very badly. Thank you for making time to talk to us. Having listened to you, I can now understand why you're in such demand and why you are so busy. Thank you very much. You went through a lot of stuff, but you know, your flow diagrams and your tables made it very easy to assimilate. Thank you very much, Chris, and enjoy the weekend. And thanks from all you guys who logged in. Enjoy the weekend, and let's go out there and fix up the water supply quality for South Africa. Thank you very much.